Assalamualaikum and good morning. Can you hear me? Assalamualaikum and good morning. Can you hear me? Hello?
Good morning, Doctor.
Right. We start our lecture by revisit what I told you last week regarding the example 1.1, where you are given open loop transfer function. Okay. With 3 open loop poles at -2, -4, and -6, and none zeros with a single key gain. As usual, the rule locus is given, or they might ask you to sketch or freehand draw. And then you have to find the gain key at 10% overshoot. This one is very easy. Just use the reference graph. No need to remember the formula. Estimate the settling time, peak time, rest time, and steady state error for the value gain k that you achieve in B. And then check the second order approximation validity and double check using MATLAB. So this is the plot, okay? Usually this plot is given in the tests and exams, real scale plot with full grid, okay? And you are required to find the gain k at 10% overshoot. So we assume for gain k equal to 1, okay? The closed loop time response is given as this, okay? Right. This one is GS. So you have to find the TS first. Okay. So the TS is G over 1 plus DS. Okay. So once you get the TS, you inject the closed loop with the step 1 volt and observe the response. Okay. So we get this as slide number 25. Okay, with k equal to 1, the gain is 1, settling time 2.42 seconds. Final value 0.02, which will produce steady state error 1 minus 0.02, which is 0.98, which is very, very big. Okay, so we need to do gain adjustment in order to improve the steady state error and to improve the settling time. Improve meaning reduce the settling time to small value, okay, so that it become faster. So for 10% overshoot, we can get zeta 0.591. This one is achieved from the graph. Okay, graph is given. Okay, or you can use formula as number 1 and number 2 shown in the slide. So with 10% overshoot, which will, if from the overshoot, you get zeta, and then from zeta 0.591, you will get the theta, the angle. Okay, so this angle is 53.77 from inverse cos. And use your protector, and then you draw the line here, okay, to get theta. And then this straight line will intersect with the root locus. So this is the root locus line. Okay, and this is the zeta line. Okay, and the angle theta is represent the zeta value. Okay, and the length from 0 to omega n. Okay. Hey. Itu nanti hilang, tutup. From 0 to this point, okay, this length, okay, is the omega n value, the length between 0 to the intersection point, okay? So that's why if you are not given a plot, okay, you just been given overshoot, and then zeta, and then omega n, you still can find the dominant poles, okay? So this dominant poles, as I told you before, is the poles that have a high influence towards the system output, okay? Right. What is the value of the gain at the dominant pole here? By calculation, by computer, it gives you 45.6. By calculations, is by using this formula, which is the gain criteria. Yes, gain criteria. Oh, off your mic. On Kuan Yin. Somebody message him. Okay. Thank you. So K will give you 46 by calculation, using the gain criteria formula, which is magnitude S plus 2, magnitude S plus 4, magnitude S plus 6. You just take this value as the dominant pole value, and you insert inside the K value, and then use your calculator. So you will get 46. Okay?
Doctor, excuse me, can I ask a question here?
Sure.
Uh, yeah, for the dominant poles, you said the only way to get the dominant poles is from the plot. So
Yeah.
you said that if the plot is not given, there is another way to get it, or it's only this way?
Okay, its plot is not given. Okay. You just use the concept of dominant pole here, where minus 2.03 plus minus J 2.77, which is equal to minus zeta omega n plus minus J omega D. Okay, so in this case, this 2.03 is equal to zeta omega n. Okay, so once settling time is known, okay, settling time is given. Previously, the settling time is given, let's say from the, is given as here, 2.42. So I use this, okay. 4 divided by zeta omega n. And can you repeat, help me, the dominant pole value, which is minus 2.03 plus J, Amro?
I can't remember the J
You can't
value.
remember the imaginary value then. Where are you? 2.77, okay? 2.77, which is equal to minus zeta omega n plus J omega D. So you can see here, the real part is zeta omega n, okay? So 2.03 is equal to zeta omega n. So you use this, okay? Which is TS is given, okay, given. Plot is not given. So plot is not given, so the is 2.42, okay? 2.42 seconds. So in this case, 2.42 seconds is equal to 4 divided by 2.03, okay? Divided by 2.03, so you get this this value, okay? So you can see that, okay, I delete this one first, okay? Settling time is 2.42, okay? And then the formula is pi zeta omega n, okay? So zeta is given as just now is 0.591. 0.591. So in this case, you get omega n. Okay. So omega n will you calculate later, which is 4 divided by 2.42 multiplied by zeta 0.591. So you get the omega n value. So once you get zeta, once you get omega n value, so you can find the point here, okay, which is zeta omega n. Okay, and this point will intersect with the root locus, and then automatically you can find the value of j omega d if plot is not given. This example is in the past year test one. I will discuss next week if we go to the question. Okay. Right.
Okay.
So another way to calculate the gain is by using the L1, L2, and L3, the length. Okay. So this length is you get from the Pythagoras theorem. Okay. For example, L3 is automatically is 2.77 because it's a 90 degrees. Okay. Yit Wang Fo off. Then L2. Okay. So L2, you just get this value. And then you got 2.77, then you get the L2, the length of this line, and L1, the length of this line. This is another way to calculate the gain K. I prefer to use this one. Okay, all my students, please follow using this one. It's much easier compared to the using Pythagoras theorem, but the choice is yours. Okay, so from the time spec, we obtain from the graph, which is the dominant pole here. Well, is equal to zeta omega n plus j omega d, right? And omega d is omega n1 minus zeta square. So this dominant pole consists of a lot of informations, okay, in design. And what you will use here is the formula for the settling time, which is 4 divided by magnitude of real, which is 1.97. This one is faster compared to previously, which is previously was 2.42. And when k equal to 1, 2.42 seconds. This one is when k is equal to 46, and this one is when k equal to 1. You can see the difference when you increase the gain, okay? And then the peak time also reduced, okay, to 1.13. Previously, when k equal to 1, we cannot see any peak time, okay? There is no peak time and there is no overshoot from the time response when k equal to 1. Can you understand what I say just now? Hello? Can you understand? Can I? Everybody sleeping.
Yes, doctor. Yeah, I can.
Stop over. Okay. So from here, say if zeta omega n is equal to 2.03 and zeta is equal to 0.491, so you can automatically get omega n value. Okay. 3.43 radian per second, or the length between 0 to the dominant pole, as I told you before in the class, which is this one, the length. Okay? The length from origin to the intersection point is the omega n, value. Then you can get rising time, which is a 0.53 second, also using the graph given. But this one very rare, as in the test and exams. But just be prepared. Some of the lecturers may really like to highlight this item. And this graph is omega n TR, which is this one, versus zeta, okay, here. And this curve is represented by this formula, omega n TR equal to 1.76 zeta cubic. Okay, and so and so. Right. The steady state error, which is from the system, is type 0. Okay, this is the transfer function s plus 2, s plus 4, s plus 6. There is no poles at the origin. No poles at the origin. Okay. So the origin is empty. So the system is type 0. Okay, due to the s power of 0. So s power of 0 is 1. So we have to use the position formula, the KP, okay, position error constant, position error constant. Okay, guys, 1 over 1 plus KP. So KP is limit s to 0, KGS. So K is 46, the one that we calculate previously. 46 divided by 48, 0.96, okay. So this one 0 lah. 0, 0, 0. 2 multiplied by 4, 8. 8 multiplied by 6, 48. And 46 is from the gain. So once you get the KP value, insert inside the formula, so you get 0.51. That is the error. Reduce. Previously 0.98 when K equal to 1. And this one is K equal to 46. You can see that reduce, which is a good improvement. Okay. In design is good lah. Once you improve, your design considered very good. Okay? Good step and good approach. So the dominant poles at K46 is given there. So third pole is minus 7.95. This one you get by using the characteristic equations. Okay, so you insert the K value, which is 46. Then you simplify this cubic, find the roots of s cubic plus 12s squared plus 44s plus 94. So you will get the dominant pole value and the third pole. Okay. So find the ratio. So the ratio of the third pole divide by the ratio of the real part magnitude is 3.9, less than 5. So second order approximation is not valid due to the ratio less than 5. So system is original third order. So approximation for second order is not valid. So we continue this one. This is the plot, okay, by computer. Okay, you can see that when you generate this one, the 0.591 is you just get the value 0.591. Okay, then add the double prompt, then S grid Z origin. Okay, then enter. So the computer will give you this line, okay, the zeta line. So this is the response when K equal to 46, okay, the closed loop. This one lah, closed loop. This is the closed loop. So we inject step 1 volt, then the response is here, okay. So time response must be closed loop, cannot be open loop. Remember that, okay? Closed loop, closed loop. Closed loop time response. So you can see that the peak time reduced, then settling time reduced, and then steady state error reduced to 0.5. So this is the observation from the graph, okay? So when we compare before gain compensation and after gain compensation, you can see that the graph squeezed to the left, which is faster in transient and reduce the steady state error. And then we do the analysis for before and after. All the 7 components, input signal same, gain changing from 1 to 46, overshoot none to 8.85, settling time reduced 1.86 to 1.86, peak time 1.29, final value, which will give you smaller steady state error, okay, reduce. So that is the last week. So now we go to the this week, which is we have another problem, which is this is the open loop transfer function. Open loop consists of zeros minus 1.5 and poles 0. Second open loop poles minus 1 and third pole at minus 10. Okay. Right. So this is the open loop transfer function and this is the closed loop transfer function. Okay. And what is this? Equal to 0. What is the name of this equation?
Characteristic equation.
Characteristic equations. Right. So question given 1.52% overshoot. Okay. So 1.52% overshoot using graph which is very, very down here. Okay. A little bit down, which will give you 0.8. Okay. 0.8 approximate. So 0.8 and then we plot the rule locus. So we have 3 rule locus path. Okay. This one. Okay. This one. One ended at zeros here, and then the other one will go here. Okay. And one over here, and one goes here. Okay. So we start with k equal to 1. Okay. Gain k equal to 1. So actually, in reality, when you change the gain from a k equal to 1, k equal to 10, 20, 100, and so on, what is the hardware that you use? We use a potentiometer. Okay, so this is the potentiometer. Okay, which have input, VCC, output, and ground. Okay, so we use the concept of voltage divider concept. Okay, so the output will be the wiper. So this is the wiper. Not car wiper, but is a potentiometer wiper. So when k equal to 1, so this is the response. Okay. Can see that start from 0 and then ended at 1. Okay. And then we draw the 0.8 damping ratio line. Okay, to the rule locus. So we found that it have 3 intersection, which is 3 dominant poles. Okay. Minus 0.87 plus J 0.66 when K 7.36. Minus 1.19 plus J 0.9 when K equal to 12.79. And the third one is minus 4.6 plus J 3.45 when K is equal to 49.64. So zeta 0.8 will give you 36.87, which is the angle of the zeta line. So we have 3 dominant poles, okay, because the zeta line intersection with 3 RN lines, okay. So we check one by one, 7.36 when gain is equal to 7.36. So we adjust the potentiometer so that it give you K 7.36. Then you can see that the response now a little bit faster compare K equal to 1. Then we increase again the potentiometer. Okay, so this is type of potentiometer. This one you rotate this one using hand. Okay, the knob, but this one you rotate using a screwdriver, where you have to turn the screwdriver, and the small device there is the potentiometer. So 12.79, much better. Okay, you can see that this one, let's say the settling time is about here, 6 seconds. This one is much better, which is at 4 seconds settling time. Okay, and then 39.64. So you adjust the knob to the gain 39.64. So you can see that the settling time is almost 2 seconds. Okay, so we can see the change when k equal to 1, 7.36, 12.79, and 39.64. So it become faster. And of course, we don't have any issue on the steady state error because the steady state error is 0 from the beginning of the gain k, 7.36, 0, 12.79, 0, until 39.64. Steady state error is 0. So we don't have any issue on the steady state error. Right, as usual, the dominant pole, the 3-pair dominant pole use this concept minus zeta omega n plus j omega d. And then the settling time and the peak time also, okay, for 4 divided by real, pi divided by imaginary. And this system is type 1, okay. Why type 1? Because the transfer function here is have one pulse at the origin, okay. One over here, one over here, minus 1, and one over here, minus 10. And zeros is over here, near to minus 1. So once you have a pulse at the origin, so the system type will be type 1, okay? And if system is type 1, you have to use the velocity error constant. You have to calculate the velocity error constant, which is limit s to 0 SGS. Okay, so you insert the k value that you get, multiplied by the open loop transfer function, and then calculate the error, which is 1 over kV. So I summarize all the 3 dominant poles, okay, with 3 different gain, right? So this is the 3 dominant poles with 3 different gains. The zeros always constant at minus 1.5. And the third pole also different because of the gain k. And you can see that the settling time is improved from 4.6 to 3.36 and 0.87. Okay, so I want to ask you which one is the best, because we have a 3 dominant pole. So which k is the best? Of course, 39.64, because it gives you a very fast settling time at 0.87. Okay, and the error is 0.17. Okay, compared to the other 2k. Yeah. So for the third pole calculation, I give you the examples here, okay, just using the characteristic equations. So you get the third pole, which is 9.25, 8.61, and minus 1.8 for 39.64. So the conclusions, the locus allow us to choose a proper gain to meet a transient response specification. As the gain is varied, we move through different regions of response. However, we are limited to those response that exist along the root locus only. So we need to find flexibility, okay, in the design, which can be increased if we can design for response that are not on the root locus board. Right? For example, if we desired transient response at certain OS and settling time, so we need to do gain adjustment. Okay. For example, from A, you want to move to B. Okay. Because it's another spec design. So we have to do gain adjustment to do that. Okay. Because point B is not on the root locus. Okay. So we need gain adjustment to do that. Therefore, the controller is needed in order to achieve this kind of response, which is the black is the best one compared to the blue. Okay. So you can use compensator, okay, but we don't teach compensator in time domain, okay? As in your book, in chapter 3, you can ignore because chapter 3 is not in the scope of the particular subjects, okay? We are focusing on the controller. And then for the controller, we usually use cascade compensation, serial, like this. So this is the controller, okay, and compensator where connected serial to each other. There is another way where the feedback compensator located at the feedback. So this one is more complicated in design, but can be done. Okay, such is a longer solution compared to the cascaded one. Right, so we end the gain adjustment. Before we enter to the PI controller, is there any question? Is there any question? Chong Lee Jun? Chong Lee Jun? Tak datang. Chua Bing Han? Chua Bing Han?
No question.
No question. Ethan, Eng Yi Juan? Eng Yi Juan?
No question. No
Yu
question.
Hoi Ni? Yu Hoi Ni?
No question.
Ho Si Lim? Ho Si Lim? Jenny Chua?
No question.
Kalway Mok? Kalway Mok? Kok King Teng?
No question.
Ko Lee Him?
No question, Prof.
Lo Zi Xuan?
No question, Doctor.
Lau Kian Yi? Lau Kian Yi? Tak datang. Lau Kian Yi tak datang. Lui Jun Liang?
No question.
Ong Kuan Yi? Ong Kuan Yi?
No question, no question.
So Jin Sheng?
No question, doctor.
So Jin Yong?
No question, doctor.
Tan Jing Chuan?
No question, doctor.
Tan Yang Yin? Tan Yang Yin?
No question, doctor.
Tan Ye Jian?
No question.
Teh Yah Jian?
No question, Doctor.
Abdullah Abdul Hadi Hussein Ashabri?
Yes, sir.
Attend. Atia Mahmud Abdul Rahman? Sorry, Amru Zakaria, sorry. Attend.
Yeah, Amro.
Astaghfirullahaladzim. What is this name? Balfakia Ahmed Salim Ahmed.
Yes, doctor.
Alhamdulillah. Chong Lee Jun. Tak datang, eh?
Yes, Doctor.
Oh, ada. Okay. Right, so we continue to the PI controller as shown here. PI controller is used to improve steady state error. So that is the general function of PI controller. So ESS can be improved by placing an open loophole at the origin and increase the system type by 1. Okay, so by this time, I hope you know already what is type 0, type 1, and type 2. Okay, you just look at the denominator. If s equal to 0, type 0. If s equal to 1, type 1. If s equal to 2, type 2. Okay, and this type 0, the steady state error formula will be 1 plus 1 over 1 plus Kp, where Kp is the position error constant as shown in this table. Okay, for type 0, this one. For type 1, we use Kb. For type 2, we use Ka. Okay? And the error formula will be 1/1 plus Kp for type 0, for type 1, 1 plus Kb, and for type 2 is 1 plus K. So Kp, Kb, Ka very important, okay, for time domain and especially for the frequency domain, because we need to calculate Kp, Kv, and Ka using formula and by using the graphical representation. Okay, so consider a system operating at the desirable response with the closed loop pole A. So by adding a pole to increase the system type, A is no longer a closed loop pole. Okay, here. So it will goes to the another point, okay, which will increase the system type and make the system error from final value to 0. So to solve this, we attach a 0 close to the pole at the origin here. Okay, so this is the origin, and this is the zeros, added zeros. Okay, or in transfer function form is here. Gain, K is gain, S plus A is the 0, which is near to the origin divided by S. Okay. So actually, this A is very, very small. Okay. So sometimes in designer use as S plus 0.1 divided by S, or some designer use S plus 0.01 divided by S. Okay. Small. Okay. 0.1, 0.15, or can, as long as near to the poles at the origin. So actually, it will cancel out these poles at the origin, because actually we are doing increment of the system type. Okay, so that from type 0 become 1, and then the error will become 0. For example, we have a system damping ratio 0.174. Okay. So the theta will be inverse cos 0.174, which will give you how much? Zero 0.174. Theo Chi Jin, what is the theta value?
80 degree.
80 degrees. Sure. So this is before compensation, before design, okay, where we have a normal gain K, and then we come out with the approach to reduce the error by adding a controller, PI controller, KS plus 0.1 divided by S. So 0.174 is over here, which will give you 80 degrees. Okay. So the dominant pole is at minus 0.694 plus J 3.926, and the gain is 164.6. Okay. So this dominant pole actually can be written in S square plus 2 zeta omega ns plus omega n square equal to 0. Okay. So once you get the zeta and omega n value, you just insert and you can construct the quadratic equation. So this is a dominant pole equations. Okay. Dominant pole equations. And the system is original is Kp, a position error constant, which is type 0, and the steady state error is calculated, which is equal to 0.108. Okay, the steady state error. Okay, so this one is using formula Kp limit S to 0 kgs. Okay, you will get 8.23, and steady state error is ESS 1/1 plus Kp. So how to calculate the third pole in the closed loop? As usual, using the characteristic equation. So this one is another way. Okay. So we take this dominant pole equation, we insert inside here as a quadratic, which is a s square plus 2 zeta omega n s plus omega n square equal to 0. Okay, this one. Then we assume the third pole as capital T, then equal to 0, and k is 165. Simplify. Okay, then simplify, so you will get the T at minus 11.6. This one also can. The other one also can. Okay, no problem. Roots of cubic. Right, so from the computer simulations, okay, we get these root locus, 3 path, okay, ended at infinity. Okay, all are ended at infinity. Okay, with the dominant pole over here. Okay, dominant pole, damping ratio, and overshoot at 57.6, and omega n is at 3.99 radian per second. So when we adding 0 at -1, so we start to design the PI controller as plus 0.1 divided by S, K and K, which is cascaded to the model, to the plan, right? So what it will do is this one, the root locus path, actually not much change, okay? Not much change in terms of dominant pole and the gain. You can see that a little bit reductions, and it's about the same, the dominant pole. Because of the zeros and the poles at the origin is very near together. It's overlap or almost overlap and cancel each other. So compensated closed loop poles and gain are approximately the same as the uncompensated system. Both give the same transient response. However, with PI, the system type has been increased from 0 to 1. Okay. Previously was type 0. Now it's type 1. So when it's type 1, automatically the steady state error is become 0. Okay. So we can prove that, okay, by using the simulations of the computer here. Okay, not much change. Okay, the third pole and dominant pole. So when we see the time response, so this is the time response before PI controller. You can see that the error is 0.108. And this one is the error is equal to 0. Okay, equal to 0. So it proves that the PI controller has already reduced the error from finite value 0.108 to 0. But you can see that after 30 seconds, after 30 seconds, the steady state error becomes 0. Quite slow to reduce the error, but it will become 0. Okay. So that's why PI is the good approach to reduce the steady state error. So we make a comparison, 2 graph in one. This one is 2 graph in split plot. Okay, but when we do it in the what do you call that? 2 graph in one plot, you can see that it reduced. The uncompensated is before design, compensated is after design. Okay, so it reduced to 0 steady state error, and the final value is at 1. Okay, 1.0. So in general, the transfer function of PI controller is given by K S plus Z divided by S. So Z is 0.1 or 0.01, any small number, okay? Any small number that is near to the origin, okay? So when you apply this, it will make the system error become 0, okay? So this is the explanation, PI controller. By adding pole at the origin, 0 is chosen to satisfy the transform response set specification. So actually we varying the ratio of Ki divided by Kp. Okay. So Z actually is the ratio between Ki and Kp. Okay. The position constant and the integral constant that will make up to the zeros value. Okay. Second example is shown here, where you have an open loop transfer function is a second order system. First of all, the system type is 0, type 0. So type 0 is using Kp, and the steady state error is 1 over 1 plus Kp. So design PI controller to achieve the transient response as follow: 10% overshoot, okay, which will give you zeta 0.59 from the graph. Okay, standard graph. Target settling time 3.2 seconds. Okay, so settling time is 4 divided by zeta omega n. And steady state error is 0. So this one you just choose this one as the PI controller. Very easy. Okay. So if you don't like 0.01, you can choose 0.1. Or if you don't like 0.1, you can choose 0.001. As long as it's a small number near to the origin. Then verify design using MATLAB. So this is the plot, two root locus path. Start from -2 and 0.5, minus 0.5. And we have a breakaway point there. Ended at infinity, ended at infinity. So 0.59, which will give you the angle. Okay, what is the angle value here? Wong Jo Yin. Wong Jo Yin.
Wait a moment ya, Doctor.
Theta berapa?
53.84.
Share 53.84. So that is your 53.84. Intersect over here, which will give you a gain 3.5. And dominant pole minus 1.25 plus J 1.71. Okay. So this is the before design, time response before design. Okay. The program to get this is first S equal to transfer function apostrophe S apostrophe. And then you write the open loop transfer function. So in MATLAB, overshoot, percentage is comment. So the computer will ignore this because it's just a comment for your notation. Yeah. So open loop transfer function, because when we say time response, it must be closed loop. Okay. So find T. T is equal to G1 over G over 1 plus G. Okay. Which is the closed loop transfer function. And then step T, step closed loop transfer function, and then grid. So you get this response. Okay. So what is the observation here? Peak time 1.84. Settling time 2.79. And error. What is the error value? Yep, Sun Yu. Yep, Sun Yu. Tak tahu.
喂啦，
Oh ya, wait lah. Tidur ke?
这样算咯。 1 minus 0.77 0.222.
Okay, thank you. 0.22, meaning there is an error. So already sketch your locus, already find the closed loop poles, already find the dominant poles. And to achieve 0, we use this PI controller. So this is the PI controller. Senangnya. S plus 0.01 divided by S. Okay, easy. Cascaded to the plant. Cascade. Cascaded. Cascaded meaning multiply lah each other later in the calculation of the closed loop and open loop transfer function. Resketch again the PI controller. Find the closed loop pole again. Not much change. And we can see that the transfer response become 0 steady state error. Okay. So this one we resketch again. So after cascaded, we multiply each other. So this is the open loop transfer function. And use the formula for the closed loop. Okay. Then you get new settling time, not much change. But Kp is infinity. Okay, Kp is infinity. That's why 1 over infinity is equal to 0. Let's say 1 over 40 million. The pulse is at the value of the denominator is 40 million. So 1 divided by 40 million, 0 lah. So this is the scenario before compensation, before error. And then this one is after PI controller. Okay, so after, how much is this? 600, After 600 seconds, so the response will settle at 0 steady state error. This is the zoom. Zoom want to see that there's still error at this time, but it takes time in order to get 0 steady state error. All right. We have a break, okay, for 10 minutes. 10 minutes break. Hello, guys. 10 minutes break. Okay, guys, we continue. With the next controller, which is known as PD controller. Okay. Can you see the slide? PD controller?
Yes.
Hello? Can you see the slide?
Yes,
Hello?
Doctor. Can see the slide.
Huh? Can?
Yes, yes, Doctor.
Okay. No sleeping, huh? So, so we already finished with P controller, PI controller. Now we enter to the PD controller. Okay. The scope for the last scope for the test 1 on the 29th of April. So what is the function of PD controller? Is to improve transient response and maintaining the steady state error. Okay. Improve transient response meaning to make the system more faster. Okay, not slower. So can be improved by adding a single 0, okay, to the forward path. Okay, just now PI added 0 near to the origin, but this one adding a single 0 to the forward path. Okay, so of the feedback control system, this 0 can be represented by GPD, KP plus KDS, so we simplify as S plus KP KD. Okay, so this one is considered as 0. So the 0 actually is the ratio of the proportional gain divided by the derivative gain. Okay. So we must do a proper selection and calculation of the zero. We just cannot choose any zeros. Okay, we must choose and calculate the zero using a proper method that fulfill the target or spec design. Okay. So look at this, the concept of adding zeros. So this is the uncompensated transfer function. Okay. So what is the open loop transfer function here? May I ask? Yep. Yeah. Sun Yu. Sorry. Yo UN. Yo UN.
Yes, doctor.
What is the open loop transfer function here? We have -1 open loop poles, -2 open loop poles, and -5. No zeros. So meaning that S plus 1, S plus 2, and S plus 5. Okay, correct. Correct, yo.
Yes, yes, doctor.
UN key, verified. UN key. Tak datang. UN key.
Yes, doctor, sorry. What
Okay.
question you asked us now?
Where are you? I asked what is the open loop transfer function from this rule locus plot. So it is k over S plus 1, S plus 2, S plus 5. Okay, because we have 3 open loop poles and no open loop zeros. Betul, huh? Sorry?
Betul.
Sorry, okay. Right, so we add S plus 2, okay, which is -2 zeros over there. Then we add -3, then we add -4. We want to see 3 situations, the different zeros value starting from -2, -3, and -4, and see the response. Okay. So this one, the closed loop transfer functions previously was k equal to 1, so we increased to 23.72. Okay. So the gain now is 23.72. This is the k value. Okay. And we observe the response, time response. So what do you observe? Peak time 1.64 second. Settling time 3.75 second. And steady state error. What is the steady state error value? 1 minus 0.7, 0.3. Okay, the error is 0.3. So we added S plus 2. Okay. We added S plus 2 zeros and see what happened. So the peak time now is 0.46. Settling time now is 1.12. Steady state error 1 minus 0.9, which is a 0.1. Okay. Then we add S plus 3. Okay. And see what happened. Peak time 0.548. Settling time 1.38. And steady state error is about 1 minus 0.95, 0.05. Okay. And then lastly, we add S plus 4 with gain 20.76. And we observe the response. Peak time 0.71, settling time 1.8. And the error is about the same, gain 1 minus 0.9, 0.1. Okay. So we make a comparison. Okay. This one is before design, before PD controller. This one is after PD controller at 0 minus 2, at 0 minus 3, and minus 4. Can you see the difference? Which one is much faster compared to the benchmark here? This is the benchmark, 1.64. So we use 3 approach. So it seems that added 0 at minus 2 will give you faster response. Am I right? Agree? Agree or not?
Yes, doctor.
Agree, eh? Compared to the other two. So all compensated system operate at a damping ratio 0.4 as the uncompensated system. For all the compensated system, the closed loopholes have more negative real and larger imaginary part. Thus, after design, it make the settling time shorter and peak time shorter. Okay. So in summary, adding a 0 on the forward path improve the transient response. A proper selections of the value of the 0 is required. So you can see that the difference here. Okay, this one is before PD controller. This one is we try to add 3 type of zeros and see. So it seems that minus 2 is the best. Minus 2 is the best. Okay, compared to at minus 3 and minus 4. So example 4, you are given the system shown here. So design a PD controller to yield a 16% overshoot. Okay, so this one will give you zeta with a 3-fold reduction in the settling time. So what do you mean by 3-fold reduction of the settling time? Meaning that the settling time mu is equal to 1/3 multiplied by TS old, the old one, the old value. Yeah, so that is the meaning of 3-fold reductions. And then check design using MATLAB. So from the graph, zeta overshoot, okay, which will give you zeta 0.5. And this one, the system type is type what? Type Yit Wang Fuk. System type. Tak tahu. Yit Wang Fuk.
Type 0.
Type 0. No, it's a type 1. Okay, because single pole at the origin. Okay. And then, so type 1 is KB. And the steady state error will be 1/KB. Okay, remember that. You still don't understand the system type concept. So please do some revisions from the last semester subject. So we have 3 open loopholes, which is and no zeros, type 1. And the 3 open loopholes is 0, -4, -6. Okay. Determine zeta and theta from the given OS. So what is the theta value? Ahmad Solihin. Ahmad Solihin.
Ya, Doktor.
Theta value.
59.73.
English 59.33. Okay.
73, Doktor, sorry.
73, sorry. So you get zeta and theta, and then determine the intersections between RL and zeta line. Find the gain value at this point. Then find the third pole. At this gain value, check for validity of second order approximation and calculate the steady state error. 1/KB just now. And identify the desired spec. Is it has been fulfilled or not? So 0.504, which will give you theta 59.73 degree. Okay. So you can use this one much better. Okay, this one no grid. Okay, no grid. So use this one, the one that I sent into the WhatsApp. Okay. So the point is here. So you will give you gain at 43.5, dominant pole minus 1.2 plus J 2.07. Okay. Damping 0.5. And this is the third pole. So we draw, okay, and then we try to find what is the settling time. So from this settling time, which is TS, 4 divided by zeta omega n, which is 3.32 seconds. So this one is a T all. Okay. And peak time is 1.52. Okay, and the error, sorry, the KB is here, KB, which is 1.8, and 1 over 1.8, so steady state error is 0.55. Okay, so our target is T new is equal to 1 over 3 T all. Okay, so 1 over 3 multiplied by 3.32, how much? Miss Tang? Miss Tang, 1 over 3 multiplied by 3.32. Tak tahu.
1.11.
Huh?
1.11.
1.11 second. Okay, so this is the new desired settling time. Okay, the new we have to design the PD controller so that the new settling time will be 1.11. We don't want 3.32 anymore. Okay, so in that case, to get this 60% overshoot, okay, we found here. So TS is 3.32. So this is the steady state error. Okay, this is the third pole. So the desired is 3.32 divided by 3, which is 1.107, as Ms. Tang said just now. So what shall we do? What shall we do? So we have to find the point lah, which is TS. See here, TS 1.107 second equal to 4 zeta omega n. So this is a real part. Okay, real. Real part of the new dominant pole. Okay. So the new omega n will be 7.17. Okay. So the real closed loop part, which is zeta omega n, which is minus 3.613. And this 3.613, okay, will match with the new omega d, which is 6.193. So this is the new dominant pole. Okay, so you get here, which is a minus 3.613. Okay, so it will hit the root locus. Then use your ruler, go to the right. So you automatically will get J 6.193. Macam tu. Okay. Because this will give you the new settling time at 1.107. So now we have to find the zeros value lah. Okay, so this one is the new dominant pole, the new one, new dominant pole. The old dominant pole will be ignored. Okay, the old one will be ignored. This one, ignore. It's no more. Okay, so this is the new dominant pole. We locate here. Then this is the open loop, minus 6 open loop poles, minus 4 open loop poles, and 0 open loop poles. And the new zeros, okay, we just put anywhere along the real axis. You can put here, no problem. 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 Okay, any place will do. Okay, as long as it is located, okay, at the real part, real axis. Okay, understand? Hello, understand that? Understand, eh? Right. So we calculate the angle. For PD is quite difficult. You have to calculate the angle. Okay, find the theta 2 due to poles -6. Find theta 3 due to the poles at -4. Find theta 4. Okay, which is unknown, and find the theta 1. Okay, which is due to the 0 poles. Okay, so what I did here is I show you to find the theta 1. Okay, so theta 1 is 180. Theta 1, 180 minus 59.7, which will give you 120. Theta 2 here using a arctangent 86.42. Theta 3 here is arctangent 68.92. Okay, and theta 4 unknown. Okay, unknown. We don't know. Then this is the angle that we try to calculate, equal to 180 degrees. So this is the angle criteria formula. Okay, so you get theta 4 95.6. Okay, so 94.6 is about here lah. Okay, about here 94.56. So the 0 is calculated using the angle property. Total angle from the poles to the root minus total angle from the zeros to the root equal to 180 degrees, and angle is 95.6. How? We already calculated just now. So thus Z is equal to 3, which is here. Okay, which is here. How I get it is I'm using the Pythagoras theorem, triangular. Okay, tangent 84.4 equal to 6.193 divided by x. Let's say the distance between the zeros and the dominant pole is x. Okay, x is equal to 6.193 divided by arctangent. So x is 0.607, and then the new zeros will be -3. Okay, -3. That is minus 3.613 plus 0.607. So this is roughly the value of the zeros, s plus 3. Okay, so insert s plus 3 here and insert the gain values there. Okay, so you will get the response as shown here. Okay, so this is the 0 open loop poles. This is the -4. This is the -6, and this is the -3. Okay, and because of the zeros, now the plot has been changed. Okay, to this shape. Okay, because of the -3 zeros. Previously, the shape is like this. This, okay, without 0, without s plus 3, without -3 zeros. Okay, after we added -3 zeros, then the shape of the roller coaster has been changed. Okay, as shown here. So the complete solutions is this one. Okay, at 0.504 zeta, which will give you a new dominant pole, minus 3.613 plus J 6.193. K is equal to 47.45, the gain value, and the zeros is here. Okay, and then this one is the third pole. Okay, and then compare. You can see that before design. So this is the settling time, which is 3.7 something, but now it's been reduced. has been reduced to 1 point something. 1 second, which is 3 times reduced from the previous one. So the PD controller structure is here, okay? KD multiplied by S plus KP over KD. Okay, so this is the zero there, which is 3 minus 3. Okay, the zeros that we calculate just now, which is equal to 3 lah. Yeah? So the ratio is KP over KD equal to 3. The gain is 47.45 and the KP value is 1.42 after we make a comparison with the S plus 3. Okay. And then you get the final controller, which is GPD 47.45 S plus 3 multiplied with the S plus 4, and S plus 6. So make comparisons. So this one is before design, which will give you 3.47 settling time. Okay. We want 1/3, 3.47, which is 1 point something. Okay. And when we apply the PD controller, so the settling time will 1.15. Okay, reduce 3 times. So we see the example 5, okay, previous test questions for a unity feedback system with open loop transfer function S plus 5. Okay, so no zeros, open loop poles, 0, -5. System type, 7, 0, 1, 2. Chai Jeffrey, system type. Tak datang. David Fan,
Type 1.
thank you. So determine the overshoot percentage and determine the settling time of the system. Okay. Design a controller to have a 50% reduction in the OS. 50% reduction. Okay. And fourfold improvement in the settling time. So meaning that new OS, what do you mean? Do you understand by this sentence? OS new will be 1/2 OS old. And settling time new is 1/4 old settling time. Okay. So we plot this rule locus plot. Okay. So by comparison, it's a second order equation, pure second order equation. So you will get omega n. What is the value of omega n? Fong Chihao, omega n.
Square root 50.
Square root 50. How much?
$7.07.
Huh?
7.07.
7.07. Okay. And zeta? What is the zeta value?
Zero point 0.35.
0.35.
35.
So you use the graph. Okay. The graph, which will give you the upper OS at 30%. Okay. Okay. And settling time, how you calculate the settling time? Ts equal to 4 divided by zeta omega n. 4 divided by zeta omega n, which is 0.35. Omega n 7.07. So we will get 0.4 seconds. Okay. Right. And then use this. Okay. So draw the zeta line. Okay. The angle is, what is the angle? Angle. O Yusheng. Angle please. Ada. O Yusheng. Betul tak? Tak ada.
Ada.
Tak ada.
Ada.
Angle berapa?
69.51.
51.
69
Okay.
0.51.
And then this is the dominant pole. Okay. Dominant pole. There you go. Ada dekat notes. So the desired is 0.4 seconds. This is the new one, 0.4 seconds. Because Ts new is equal to 1 over 4 multiplied by 1.6 seconds. So 0.4 seconds. Okay, the new spec. So we give you the new omega n, 19.49 radian per second. And it will give you the new real part dominant pole, which is minus 10, and the new imaginary part, which is J 16.73. And the new dominant pole will be minus 10 plus J 16.73 in order to fulfill the settling time, 4 times reductions, and overshoot to 50% reductions. Okay. So this is the new dominant pole. Okay, so plot it. You have to draw this. Okay, sketch. Theta 3 is due to the zeros. Theta 2 is due to the poles at -5, and theta 1 is the angle due to the zeros open loop poles. Okay, do the calculations. Alpha 1, which is this one, 180. Alpha 2, which is this one, 73.76. Calculate the alpha 2. Then tangent theta 3, which will give you the x value, which is between the zeros and the real part of the dominant pole. Okay, take the magnitude, not the negative. Okay, take the magnitude value. So what I did is use the angle criteria. Then you get the theta 3, which is 47.51. And use this angle to find the x, 16.73 divided by tangent 47. So you will get 15.32. And the distance, so the z value is at minus 25.32. Okay, which is here. So this is the PD controller, S25.32, plus the gain K in front of it. So the gain K is 15. So the PD controller will be S plus 25.32 multiplied by gain 15. Okay. So this is the ratio, this is the Z. Okay. So K is 50 multiplied by KD, KD is 0.3. So this is the final values. Then we check, okay, is it fulfilled? The spec design. Okay, settling time 1.55. 1.55. Okay. Overshoot is 30.5. This one is before, before. So before 30.5 divided by 2, 15%. This one divided by 4 is about 0.4 seconds. Then after PD controller, so you can see that is 22.5. Reduce a little bit. Okay. And then this one is 0.384. It's about 0.4. Okay. But this one can be further down. Can be further down. But the important thing is pass lah, 0.4 seconds. So we stop here. Stop here. Tomorrow no class. So we're going to do revision next Monday. Okay. Next Monday. Any question? Any question? Attendance check. Johan Bong. Johan Bong. Tak datang. Ko Chun Sen.
Yes, doctor.
Lau Shi Ho. Tak datang. Liming.
Yes,
Li
doctor.
Ming. Liming datang.
Ada.
Lim Kim Yung.
Yes, doctor.
Lai Yong Xiang.
Yes, doctor.
Martin.
Yes, doctor.
Faizuddin. Faizuddin.
Yes, doctor.
Haziq.
Yes, doctor.
Ada. Neo Chi Chia.
Yes, doctor.
Shalom. Ada. Sun Jin Liang. Tam Shu Yi.
Yes, doctor.
Tam Hui Ting.
Yes, doctor.
Teo Jian Basil.
Yes, doctor.
Tung Kim Her.
Yes, Prof.
Wong Weng Jin.
Yes, doctor.
Yap. Chin Jun.
Yes, doctor.
Kim Wei Lian.
Yes, doctor.
Yao Fu Yi.
Yes, doctor.
Okay, thank you very much for your attendance.
Sorry, doctor. I'm Lau.
Any question? Yes, sir. Lau?
Yeah. Just now I have answered you, but I think the mic is got some problem.
Okay, Lau.
Yeah. Sorry, doctor.
Betul.
Yeah, sorry, doctor, I'm Jeffrey.
Jeffrey.
Yeah, maybe
Try
the
Jeffrey.
connection.
Okay, try again. Okay.
Doctor,
Yeah.
me and Abdullah was trying to ask about the test one, where it will be covered up until which chapter or which.
So far, we from the course information until PD controller, but 1 week or maybe 1 week before the test, the coordinator will make announcement. So at the moment, we assume until PD, and the revision will be test 1 next week. Okay.
Oh, okay, thank you, doctor.
Q1 and Q2. Thank you, Omar. Okay, thank you very much. We wish you happy Hari Raya, Selamat Hari Raya, happy holidays, guys.
Okay, Prof. Selamat Hari Raya.
Okay, Arab brothers, selamat lah, insyaAllah. Any
Eid
question?
Mubarak.
Eid Mubarak. Shukran jazilan.
Doctor,
Yes, saya.
can you share the latest,
Latest slide.
okay,
okay,
along with your
okay.
annotated
But
slide?
that is not the
Can
update, just a temporary update. Okay, I will share. And the YouTube link of today's lecture, recorded lecture. Okay, thank you very much, guys. Okay, thank you,
Thank you, doctor.
All right.
Okay.